This is the brief on dual basis vector decomposition. So, drawing from reciprocal relationships in dual basis vector decomposition, we're going to look at something pretty fundamental. How do you measure things accurately when your coordinate grid is, well, skewed? Think of it like trying to use a crooked ruler. Okay, first takeaway. The standard tangent basis vectors, those are like the skeleton that builds up a vector. But the dual basis, that's the special scanner we use to read it. You can picture these dual vectors as directional filters. To get the actual measurement, what's called the contravariant component, you just use a simple dot product. All right, second point. So how does this filtering actually work? Well, it's all because of a really strict perpendicular rule. See, the first dual vector is set up to be perfectly at a right angle to the second grid line. This makes it completely ignore any contribution from that second line, sifting out only the component you want. And finally, this is where it gets really interesting, dynamic compensation. What if your grid lines start to collapse and squeeze together? The dual vectors don't just sit there. To keep the math honest, they have to react. They rotate outward and stretch out, sometimes getting way longer. It makes sense, right? If the space is shrinking, the measuring stick has to get bigger to keep the scale correct. So in a nutshell, even if the building blocks of a vector get warped, the dual basis adapts to keep all the measurements precise. It's just a really elegant concept, geometry basically finding its own way to balance the equation.